righty. So the numbers are coming up quick, so I think maybe we'll get started. I'm going to just take a quick moment. Thank you, everyone, for joining in on the webinar. This is a series that we've got. It's been ongoing now. Started with COVID as a way to stay connected to our customers. We had tremendous feedback on the success of the webinar series. So we try and present a different webinar every month, and the numbers have been quite strong. So thank you for your participation today. We've got Trent Runyon, the president of DSS Valves, with me, and Ross Waters, the chairman of the CGIS board, and our international business development, his double hat, amongst other things. And my name is Dave Friesen. I'm the president of CGIS. And we also have Sam Wynn online, who will be making sure that we don't get messed up too bad. So throughout the webinar, feel free to ask questions. During the presentation, we'll either answer them as they come up, or Sam will be monitoring the Q&A. So if you want to click on that little button on your bar and type it into the chat, the chat bar, then we will make sure that we address things throughout the webinar, or if we know that they're coming up, we may ignore them. And then if there's anything that we absolutely miss, you can contact us through our emails as well. A little bit about CGIS and DSS Valves. There's a couple of our locations. So CGIS presently has operations across Canada. This is our Vancouver office, one of our larger automation and inventory centers, as well as service. We have a similar facility in Alberta, a little bit larger, where we really do a lot of our service work, but we see service as an integral part of the support of any product, but in particular the knife gates, where we know that they're going to be in challenging services, especially the ones we're going to talk about today. And then the DSS valves, their new state-of-the-art building they moved into a couple of years ago. So DSS, a relatively new company, 7 years old, but more than 30 years of history between their team. Trent and others have worked in the knife gate space for many, many years. So, and that because of that, we've seen rapid growth. So this is their second building in only 7 years. This one 5 times larger than the first. And there's an opportunity here with space that the land sits on to easily double the size of the current facility. So lots of opportunity for growth and success. CGIS has experienced our own growth over the number of years. We partnered in with a company called DHB Valves. So a lot of our valves and service in Quebec is done through our partner company, DHB. DSS Valves International is as the name would indicate, it's the international sales and support arm that outside of the continental US and Canada represents the DSS products and sells both the knife gates and the check valves around the world. And then our most recent addition, the Nova Hydromet Group. Ross started down a path in the hydromet space more than 20 years ago. And we recently decided to make a change in that space so that we could get more focus and allow some partners to join in, where we've launched a new high pressure letdown valve that we're actually manufacturing. But as part of that, the knife gate has been an integral part of the launch of that company. So we're quite excited about that. So the webinar today is utilizing the guided shear gate design in mining and mineral processing applications. So again, thank you for joining us. A little bit of the agenda. We're going to define the severe service valves, the 5 types that are commonly used. When you say knife gates, people think of a lot of different things. We want to make sure that we identify those and give a clear language. The guided shear gate is the latest generation of product that's in this marketplace. And we want to talk about the specific designs, and Trent will do some of that. It's always for us, the application dictates the valves is common language around CGIS. We want to talk about the applications where we have had tremendous success, and some of the other designs are more challenged. Some of the inherent issues, abrasion, erosion, corrosion, slurry, tailings, paste, pregnant solutions, all different, present different array of challenges. So we need to understand in each phase what that would look like. And then the problems with the guided shear gate design, what it solves. So how do we best address those things? And then some of the experience and case studies, and of course, always a Q&A at the end. So we're going to start with defining the severe service valve. And this is language that's come out of, a lot of people are familiar with MSS. Part of the challenge that CGIS found when we started selling in knife gates into this marketplace was that the current standard MSS SP81, which covers 150 psi and lower, was the only knife gate standard that was in the marketplace. And so that created a challenge because at the time, oil sands and other parts around the world were routinely using valves and had applications in excess of 150 class pressures, so even higher than what is covered under SP81. So in his work, Ross became part of the committee member in the 135 group. So we're involved in the development of the class 300 and class 600 standards covered under MSS SP 135. And then more recently, Ross initiated with MSS this newest standard, which is ready to be published, we hope, this coming year, which is the guidelines for classifying the severity of valve service conditions. And it identified 3 different types of families, if you will, of valves: the general purpose valves, fit for purpose valves, and then the severe service valves. And so through that work, we developed sort of a continuum, if you will, to understand how do you start to differentiate it. And really, a lot of this discussion around severe service is getting clear language. That is the problem that exists. In my favorite one, butterfly valves use high performance. I'm not exactly sure what that means. To most people that are in the market, it's a double offset, but people have they coined various terms, and it becomes challenging then to compare like products or unlike products in any way that's useful for the end user. So some of the things and the characteristics that really start to help us understand where a valve fits. So you'll note that all of these bars transfer from dark blue on the left, which is your general purpose valves, into a fit for purpose in that sky blue type out, and then on the far right, the gold or yellow severe service. So some of the things that we look about is the consequence of valve failure. The reality is, if you've got a valve that fails in an application and there's no real concern around for loss of equipment or perhaps safety, then what do we really, can it be considered severe service? And the answer is probably no. So we look at the consequence of the failure: long-term isolation required, or is some leakage available, or does it absolutely have to be drop tight? We start thinking about perhaps hydrogen isolation is a big one today. If we've got a fire and we're feeding hydrogen to a particular unit, do we really want a little bit of leakage past that valve? The answer obviously is no. So process data required to supply. Some customers call us for a class 150 carbon steel ball valve. And in some applications, in your general purpose applications, that can be fine. But if we take that same process and we want to define a little bit heavier, the further we get along that continuum to really dig into the application and ask a lot more questions so that we can ensure that we get the right one. Purchase price: typically your general purpose valves are going to be a lower cost than your severe service valves. The availability: typically more engineered versus applications on the severe service side with more options included, whereas the general purpose valves would be stocked as is on the shelf. And then cost effective to repair or replace. Again, in the general purpose sense, you would probably just simply replace that valve. In a severe service sense, you would probably look to repair it. And not only that, what we do at CGIS is we look to learn from that failure. So the 6 key factors that we looked at when we started to differentiate the severe service valves, these are probably the most critical application questions that we get into with customers: frequency of operation, the pressure, the presence of solids, the temperature, whether it be high or low, the corrosive nature of the material, and then what is the associated cost with the failure. And what is important to understand here is anytime you've got one of these criterion working on their own, you can apply virtually any technology to that valve typically, and it'll work. But anytime you start to take any two of these and put them together, then it moves up that continuum towards a more severe service application. So I could take a 1500 PSI service and I can use a Teflon seated ball valve in it and it'll last many years probably. But if I take that same 1500 PSI service and I introduce the presence of solids, well, now that same Teflon seated valve that I intended to use will probably not last very long. Or if I make it extremely hot, it's not going to work. So there's various things that we're going to look at. So in order to develop that, CGIS has probably about 6 years ago developed what you see on the right, our application severity checklist. That was part of the work that came out of Ross's work in preparation for the MSS group. But we're actually working now to make this an online tool, which will be available here through Sam and the marketing group in the coming months. So we're excited about that opportunity because it helps to clarify some of the language. Last one before I turn it over to Trent for a little bit is the knife gate valves used in mining. And I wanted to understand or explain to folks because it's incredibly challenging for us to support clients when this understanding is not present, because not all knife gates, like probably the best analogy is cars. A Lamborghini and a Lada are both cars. They both have a motor, 4 wheels and 2 doors, and you can get in and out of them and they'll move you from A to Z. But they are completely different in terms of performance. And so we have to understand what we need a valve to do, what we expect it to do. So if we start on the far left, the conventional knife gate, which was the SP81 knife gate, some of the more popular names, the Staff Joe, Bray, ITT, and Zurich, that was really a low pressure valve that had a known and allowable leakage rate, 40 cc's per inch of diameter per minute, that allowed those valves to leak a bunch. You start putting those in heavy slurry solids or concentrations, and the valves could not close, could not seal or affect a seal unless they bore or filled up with dirt at some point, and then maybe that created a block. The through gates was an expansion of that product and aimed at managing solids in a better way, particularly in the pulp and paper business. That's where they came out of. Again, some of the same players that we saw in the original design, so they were starting to be tweaked. Then we started to see in the mid-1950s lined knife gate valves. So these were less noble materials, carbon ductile materials with linings of perhaps titanium or other more noble materials. And this was aimed at the use of applications, again, in pulp and paper, typically bleach stock, where we were starting to add chemistry into the process piping. The push-through knife gate made common and well known by Clarkson, but Weir, Bray, Zurich, and ITT all have various options. This was the 2 rubber seats where you push the gate through that. They became very, very popular in the mining space in particular. What we consider hard rock mining, so where you've got very small particulate. They were used in that space. And one of the challenges that they have in particular in today's world is that there is as the valve strokes, it pushes material, and Ross will talk about that a little bit later. And then started the development of the guided shear gate. So Gen 1 through 4, Way valve, the Delta, which became Weir, and ITT. There's also a number of other copycats that have popped up over the past few years in this space. So this is when we started to see higher pressure applications. Class 600 became more readily available for sure. And then the last and most common or newest generation is the DSS valve, where Trent and his team has taken this through class 2500 now designs. And we are successfully employing them in class 915 in slurry circuits around the world presently. So it's been a tremendous growth period for us and a lot of excitement, and there's new opportunities every day. All right.
Great. Well, thanks, Dave. Appreciate all that. Kind of like what you said, is the knife gate valves have evolved over the years to where we're at with our Gen 5 guided shear gate. And as odd as it sounds, you think of a knife gate, it should be able to cut through solids, but some of the previous designs are unable to do that. And so our guided shear gate is specifically engineered to cut through solids. So when solids are in the pipeline on lesser valves, oftentimes those weren't designed to hit those solids. And so the gates would deflect and would cause problems with sealing. And so then the valves wouldn't seal at all. So we've designed the DSS guided shear gate for the most severe service applications, so that when it does hit solids, when it is encountering erosive, corrosive applications, that it continues to seal. So 100% leak tight seal is what we're after. So we have a little video here that we can roll next that kind of shows you, walks you through our technology a little bit and how it works.
All DSS valves utilize a guided shear gate design. This enables them to shear through solids, scale, fiber, and other media found in the pipeline, while maintaining bidirectional, zero leakage isolation. The guided shear gate design consists of two key elements: a shearing tip and internal gate guides. From open to close, the gate is guided the entire way, removing any option to deflect when solids are encountered. When material is struck by the shearing tip, it is fractured and angled away, enabling zero leakage where the gate meets the primary resilient seat and secondary metal seat. A secondary seal further eliminates any possible leakage to atmosphere. Our severe service knife gate valves reliably and repeatedly shear through solids, scale, fiber, paste, and any other material you can find in a pipeline. Learn more by visiting dssvalves.com. We look forward to working with you.
Talk a little bit more about some of the design in our discussion. I guess we'll talk a little bit about this right now first. So as mentioned in the animation, this is really the meat and potatoes behind what makes our valve successful. So the oversized gate, as I mentioned earlier, some of the conventional knife gate valves didn't have a thick enough gate. They weren't designed to meet solids. When they do, they deflect. They're not fully guided. So as we mentioned, our gate is fully guided through the entire stroke. So it can't bend out of the way and then cause sealing issues. We have our primary resilient seal, you see down there on the left, and then a secondary one which eliminates leakage to atmosphere. So our valve design is a split body design. We want to make sure that everything is retained inside the bore and nothing leaks to atmosphere. And then we have a secondary metal seat that you see over there on the right. And then of course, the key part to the guided shear gate is the shearing tip. So we can coat the tip of the gate with some other things like stellite or chrome carbide weld overlay to make sure that holds up in some of the severe applications that we like to guide our valves to, especially in mining.
It's interesting though, Trent, I think, right, your 17.4 gate, which we use a lot in mining, is precipitation hardened. So it's about the same hardness as stellite when it is in its finished state, correct?
Correct.
Yeah. Okay. All right, we're going to get into a little bit of the discussions right now about the some of the applications that we see. I think probably the biggest area of growth has been the slurry transport system. So this has been a world dominated for many, many years by the metal seated ball valve space. And so metal seated ball valves were used extensively because of the higher pressures. 600 and 900 were very commonplace. And these particular large designs, you're pumping materials several hundred kilometers. In some cases over rivers and other sensitive environmental areas. So metal seated ball valves became the valve of choice. We believe, honestly, that they will continue to have a space in this place, but there was also lots of applications, drains on those same pipelines, feed lines associated to them, choke stations, rupture disc isolation, instrument isolation, things where the added cost related to a metal sheeted ball valve didn't make a whole lot of sense. And then some of the isolation points around the pumps as well. The next one is autoclaves, and I mentioned earlier the hydromet space. So feed circuits, liquor heaters, flash steam, These were areas where Ross started selling valves, and some of our other partners or people in Australia starting valves into the autoclave space, and saw tremendous growth there. Mineral concentrators has become more and more important as the world continues to find and seek more metals. The concentrator business has gone crazy, and we were working with some of the manufacturers now to try and optimize their process and their equipment. So thickener underflows, the discharge isolation, filter press isolation. Ross is going to talk a little bit on the application there, very high cycle application. Slurry transfer systems, and then the cyclones. We do a lot of that work, in particular in oil sands as well, but hard rock mining around the world. And then again, from an environmental standpoint, waste disposal obviously critical these days. So what does the tailing circuit look like? What are we doing with the material? How are we reclaiming those tailings over time? And then an area that we've seen massive growth in the last few years for CGIS is the paste backfill world. And so much so that, and Trent will talk about it in a little bit, they've developed some specialty products for specifically for paste backfill applications. And then on the lower pressure circuit side, we see solution mining. So this is taking heaps of ore, if you will, and then pouring various acids on top of the pile and leaching out the constituents that you're trying to secure, and then reclaiming those in some fashion. So we're seeing that not only on the metal side, but we're also seeing it in the potash business. It's a big business that's growing around the world with our population approaching 9 billion and the need to feed more people effectively. So just a general mineral processing flow chart, what it looks like. So at the early stages, are we looking at a mine and shovel application, and then resulting? Is there going to be a backfill circuit built in this plant, dewatering, the crushing grinding circuit, concentrate pipelines, flotation circuits, thickening circuits, filtration, the concentrate pipeline, and then the finishing product. So really, we can be seen across any one of these areas of the plant. Some obviously more. If we talk about the concentrate pipelines, for instance, we're probably going to see a greater agglomeration of valves or the cyclones, but we see them all over the plants. Ross, I don't know if you want to talk about this one, maybe.
I think for us, we, as Dave said earlier, we're very driven by the application itself. And so our world of mining includes this other thing called mineral processing, and we divide it up quite specifically because of the nature of the processes. And if you looked at the previous slide, that was what we'd call the upfront concentrate type mining, more simple, not as much process variation, versus this other world called hydrometallurgy, where we've got a lot of different and complex processes that are not the same everywhere. We've broken them down, as you can see, into different pieces. The pressure hydromet is one where I particularly love to live, and that's what includes having an autoclave. And on the autoclave, there are some really difficult applications that challenge every valve. But we want to play in here because the nature of the design, the guided shear gate, it has all these wonderful benefits. It's zero leakage, bidirectionally equal. It doesn't discharge. It doesn't emit to atmosphere, so it's clean in an environment that needs to be clean. And we have a tremendous history that started for us in a little town in Trail, British Columbia, at a place that used to be called Cominco, but now it's Tech Metals, where they had a lot of different hydrometallurgical circuits that we learned from. From there, we've gone around the world, and I would think right now we can make a pretty good claim that we are the leader of selling knife gate valves into hydrometallurgy globally.
Great. Thanks, Ross. So these are some applications, and again, I might bounce back and forth with Ross, but the reality is that the choice of knife gates can be very difficult, as I mentioned earlier, and sometimes some of the really critical components that are within a process are not understood, or the ramifications aren't considered fully. So some of these applications, the one on the far left is a valve, and what you're seeing there is a weak acid that is eaten through the body of this valve. So you've had some leakage out the valve, and it's started to erode the outer body. The seals have failed, and now this is a raincoat that's been wrapped around the valve to stop this acid from spraying on passersby while they get to a maintenance condition on the valve. We've also got several other pictures where the top structure on the valve was eroded to a point, or corroded rather, to a point where when the actuator fired, it flipped the actuator on the floor next to it. So obviously a lot of concerns around that. So in this particular case, when you start dealing with acids, yes, the seal of the valve is critical, but also the thing that holds the seal, or the body and the gate, are particularly important. And sometimes people find it advantageous to save on that so that they can put the money in the seal. This is the effect of that. We see this all over the world. This one here, this is one of those valves I mentioned earlier that discharges, free discharges on every stroke. So that's what you're seeing here. Again, this is weak acid. This is about 3 stories, as you can see, 3 stories up in the air. And this is flushing down on the passersby underneath. So this became an emergency quickly and was replaced by one of our valves. This is a valve from one of our clients that Ross mentioned earlier. So this is when solids come out of suspension or a pregnant liquor solution. What happens? Temperature changes, and then it turns into a solid. So this is what happens when you put a valve in that doesn't seal 100%, is not zero leakage. Then this can happen. Bottom one I actually have not witnessed or seen, but that to me looks like a failed diaphragm valve. But
Dave, it's behind that is coming out from a push-through knife gate valve. That's it.
Okay.
That's up north in your, in your province.
All righty. Thank you. So critical things that we consider: abrasion, the act wearing away. So when the abrasives are hard, then obviously this could be accelerated, or the actual velocity of those fluids could be a problem. So some of the questions we're going to ask about is, what solids and how much? So what are we dealing with? What is the nature of it? Is it more like peanut butter, or is it little rocks, or is it little rocks with big rocks? All those kinds of things. So is the material light enough or in a low enough concentration that it's likely to stay suspended, or is it in heavier concentrations at lower velocities we're going to see sliding bed type erosion? These are the kinds of things. So when we start talking about tailings and concentrates and paste systems or thickened tails, we're going to try and understand what those challenges are, whether the material itself is in a dissolved state where it could potentially come out of solution. We're going to want to understand all those things. So it's important for us and for you as an operator, if you want to be successful, to understand the nature of what you are dealing with. One of the things that we've recognized, I think probably in the last 10 or 12 years, we've seen a big push in Western Canada to the use of groundwater. And so we're seeing chloride levels and whatnot that weren't necessarily present 5, 6, 7, even 10 years ago, is starting to become more of a challenge. So whereas, carbon steel, stainless steel perhaps was the metal of choice in past, we're seeing more of a call for duplex materials, which we manufacture in stock. So. And then what are the things that we really need to be concerned about when we're looking at erosion? So I mentioned earlier the percentage of solids, the size of that particle, the shape of the particle. I found that out through my extensive oil sands work over the last 25 years, is that the particular shape of the particle in the oil sands varies from mine site to mine site. And so we see different challenges depending on the plant and where the ore is being extracted from in the mine as well. The hardness of the material that we're dealing with, and its adhesiveness, does it stick together, can be a challenge, presents a whole different set of challenges. Is it in suspension? And what is that impact angle? Particularly, and we see that when we start talking about, there's choices over the years. Do you use soft? So you see lined rubber pipes. You see valves with rubber linings in them. But then if you get a large rock traveling at high velocity and hits a piece of rubber, you see the rubber getting torn or chunked. And so we have to understand all those parts. And understand again, some of the things that we look at. The periodic table is useful for understanding some of the constituent metals that we see on a regular course of business, and we have to understand their presence in that slurry, and then be able to, from that, make our determinations, calculations based on our experience. And this is a little bit further to some of the understanding. So bottom left is copper magnified. Top right is its normal size. Ore feed is the one to the bottom right, and then magnified obviously in the central picture. So you can see, I mean, you think about the challenges that a material that has all those crags and valleys and whatnot, traveling at 3 or 4 meters per second versus 15 or 20 meters per second in concentrations of 60% or larger. You could see how that would be just destructive to any metal surface, or any surface, in fact. So
Hey Dave,
yeah.
sorry, just real quick, while you're talking about 60%, there was a question that came in. Would DSS shear knife gate valves be suitable for phosphate slurry at 60% concentration?
Yes.
Yeah.
Okay, thanks.
Yeah. Yeah, it's a big business for us, is phosphate. So yeah. The impact angle and energy transfers. This really talks to what I was just talking about. So what are we dealing with? The velocities always play a key role in this. And when you understand the rheology of the piping system, then you can start to understand the effects that the velocity is going to have on the materials of choice, and how we set the valves up for success. So these are some of the things that are taken into effect, and we deal with people like Patterson and Cook, and piping people all over the world, understanding the challenges they have. So some of the things that do happen from time to time, and we see, and why it's important to understand these things. I talked about metal seated ball valves a little bit earlier. That's what you're looking at in the top two pictures, and applications where the seat, which was not hard enough, failed, and that created these failure points within the valve design. So you see the effects of abrasion on a metal seated ball valve, and erosion on the top right. So that's where a coating has failed to stay in contact with the ball. So the coating has failed, and when the coating fails, so goes the valve. Last one was talked earlier about sometimes people using a less noble material. What you see in the very central picture, the small little scrap, is what's left of the disc. This was a Teflon lined disc used in a weak acid wash. What was determined is that the Teflon lining was damaged, and its core material inside was I believe it was a carbon steel, if I remember right, but it quickly, the weak acid eroded the base material very, very quickly. And this is what was found. That's when the valve was opened up, or the pipe was opened up, after a very short period of time. So it has to be consideration for the likelihood that that lining may get damaged. And in that case, then the choice of a more noble material would be preferred. It's a little bit about slurries, tailings paste, and pregnant solutions. I know, Ross, I don't know if you want to talk to some of this. You've spent a lot of time with the folks at Patterson Cook. And
yes, we wanted to get from their perspective how the industry identifies these things that go into this thing called a slurry. So I asked and got permission to use these next couple of slides so that we all can be on the same page. And it helps us ask those questions to our potential clients. Where are you in this spectrum, the rheology? So this next couple of slides, if you want to go through, are just showing how the solids in solutions can be very, very different. So here we got a conventional tailings on the left, which is a lot less paste-like, if you like, to the ones that you say on the right are almost completely solid and free of any fluids. It is a continuum, and we now have a mechanism of putting it into these slots, and then from there, understanding what is the best technology to apply so that these things that we see don't stop us from performing.
I think it's fair to say too, Ross, that the conventional tailings on the far left was the mine solution for many, many years. Throughout its early days of generation, that was how people dealt with tailings, is that it simply went into a large pond. And there's been a lot of challenges over the years with those ponds, regardless of what industry or what country it is in. And so we've seen a lot more work on thickened tailings and paste and getting to a place where they can recover the solids out of those materials quicker, and then use it in a lot of cases for construction mechanisms around either the plant site or industry in the area. So
yeah,
I think that's been a huge change we've seen in the last 2 decades anyways. I mentioned earlier the pressures, they continue to grow. So class 2500, we're seeing now pretty readily in the piping, or sorry, in some of the applications in the mining space. Obviously, we do a lot of work in other industries, so it's not high pressure for us. But if you talk to knife gate people 20 years ago, anything over class 150 was becoming around for sure. But I think we sold our first knife gate of a class 300 nature into the oil sands was sold in 1998. So it's not that long ago, really, that that really started to take a place. And so prior to that, it was really metal sheeted ball valves that were the valve of choice in these applications. And the other thing that I mentioned earlier is that the pipe diameters continue to increase. So we're routinely seeing valves now in excess of up to and including 40-inch or 1,000 millimeters.
And this, I think I was going to jump in here. So we've got a term here, low pressure. It's a subjective term. Prior to 2010, there was no standard for any knife gate valve other than SP81, which was limited to 150 PSI or 10 bar. And in 2010, a bunch of us who were upset that there was no other higher performance standard approached MSS and challenged them to write a new one. And they did. They took it up. And we created SP 135 first in 2010. Then over the years, we've been added to it. But as it started in 2010, it included class 150, so 20 bar, and also class 300, 50 bar. So it was quite a big change. And the other big change was it didn't allow leakage because we tied in API 598 as the required test. So now we went from this SP81, which allowed a lot of leakage, 40 cc's per inch of diameter per minute, and low pressure, to a higher pressure, class 300, with zero leakage. So that was a good start. And that pushed the definition of low and high pressure for knife gates into this now a dichotomy, 150 PSI or class 300. In 2016, we continued to push, many of us, and we got MSS to rewrite or amend SP 135 and include class 600. So now that's 100 bar, 1500 PSI roughly, and that is our new definition. However, I wanted to be clear that not all valve manufacturers who produce a valve called the knife gate of the types you saw earlier are capable of this. And it is still a challenge. For DSS, it's not a challenge. As Trent has said, and we have shown you, we're well beyond this. MSS has not accepted that we push it above class 600 today, but I was at the annual meeting 2 weeks ago and we've challenged them, why not? And so there is talk and discussion right now, moving it up through class 900 and maybe 1500. But in the other world of valves, outside of knife gate valves, our internal definition is 600 and less is low pressure, and above class 600 is high pressure.
Some of the challenges that we see, talked earlier about what is this was a water line. So customer gave us an application on their water circuit. This is the results of a few months of operation. And what you're seeing here is some salts coming out of the solution and sticking on the side of the pipe. And this would continue to grow to the point where you would end up with a 1-inch diameter hole inside the pipe at some point. So you had to be able to manage that. And we did that with the guided shear gate technology. We're able to crush through this material and keep the valve operating reliably. But this is when people say, oh, it's just a water line. This is what it could be sometimes. Ross, I don't know if you got any applications.
Yep, this is in Panama. This is a copper mine and sending the concentrate to the port to be shipped away. So one of those lines, the one on the right, is the concentrate. It's a class 600 piping system. The one inside that to the left is the water return. So we are able to do some magic on this, and Trent's team really did some magic on this. We accepted this order with another manufacturer in August of 2016 with a drop dead delivery date of January 12, 2017. And on October, we were told by this manufacturer they didn't know, they could not meet this delivery. So at that point, with only a few months to go, we were desperate because we had huge LDs. We went to Trent and said, Trent, we got a problem. He said, no, you don't. And we replaced the order with DSS and we delivered on time. It was a pretty amazing, I'm still awed and amazed by it and thankful because I didn't lose a lot of money. So on this project was both the single block and double block and bleed valves, 6-inch and 8-inch class 600s, I think around 40 units. And since then, they've all been working very well, with one exception that was not the valve's fault. When they cycled a hydraulically operated valve with the lock pin in place. Luckily, though, the valve was built properly enough that it didn't damage the sealability of the valve. It did bend the yoke a little bit, which we fixed quite easily.
Concentrate pipelines like that are a common application for us. So we often see this. They don't put the mines next to the ocean for some reason. So typically they got to move the ore from several hundred kilometers away, or in some cases they need to get the water from the ocean to the mine site. And so we're routinely involved in applications that are very high pressure where we're moving these materials several hundred kilometers.
Hey, Dave, sorry, that's just a great segue to a question we had. Says, in several corrosive environments, how do you prevent gate damage or gate jamming? Here in Baja, Mexico, we are always near to the sea. Besides, almost processed fluids are corrosive and many of them generate incrustation on conventional gate valves.
It's a great question, and it's going to be part of my answer, but the quick answer is that we are very good at picking the right metallurgy for the construction of the valve, body and gate. So from a metallurgical point of view, corrosion resistance, we're very practiced and very good at that. Then you've added in this other issue of incrustation. And that's a secondary learning skill that we've learned over many years, targeting these applications that have, in this case, unbelievably bad scale. This is from a potash mine in the United States, where you can see the precipitation is incredible. Now, our design is capable of cutting through that, provided we know that's what we got to do, and we provide the horsepower to whatever the operator is. And in this case, you're not going to operate a valve. This is, I think, an 8-inch valve. You're not going to operate it with a hand wheel. It's not humanly possible, but we know how to make it work. So just give us your chemistry, give us the fact that you've got incrustations. We're going to ask you some further questions, and then we'll be able to solve your problems.
So I think that's where we commonly see this. We won a very large project a number of years ago, a mining project, a potash job. And the instrument engineer contacted me during the review bid process and said, I don't understand. He said, I've got 4 bids in front of me and only you have differentiated several applications on the project where you have the same valve, but you have different actuators on them. And the reason was we understood, based on where they were going to be inside the plant, that some places would see this development of solids and would need more motive force to drive that gate through it. So as Ross mentioned, if I've got a valve that I know I'm going to see large rocks and I'm going to see the buildup of solids, then I'm probably not going to be using a manual valve very often. I'm going to go to a pneumatic actuator, and if I know that it's going to be extremely aggressive, I may even suggest the flexibility offered by a hydraulic actuator, where we can put tremendous force at that tip, because it's a perfect, the body and the gate create a shear. And as we all know, the important thing about making a shear work is sufficient force to drive it through the material. So, so that's why when you look at ours, you'll see options for 1 or 2 sizes, in some cases, a larger pneumatic cylinders, and that's why. Another one, this is very common in the paste system. If they don't keep the material flowing, it ends up in this kind of a situation. So these are the areas where we again are involved in understanding what's going on inside the valves, inside the piping process, so that we can deal with these blockages. Trent's going to talk a little bit about the family tree.
Thanks, Dave. Certainly covering a lot of information there and some good questions. And I'll talk a little bit about that now, about our product. So you see here the Guided Shear Gate family tree. So all of it originates with the valve in the top, which has our new technology that's been developed over the years, right? So we talked about the history of the knife gate valve, and basically taken what we've learned over the last 100 years and built the best guided shear gate available. And so as you see here, all of our other product offerings, it all comes with the same technology that's in our guided shear gate. So working from left to right, what you see there on the left is the double block and bleed valve. That's one of our most robust valves that we make here. And it contains all the guided shear gate design, as I said. However, this one's designed to MSS SP 152. And the great thing about this design is that it eliminates the need for a multi-valve system, thus saving cost, time, and space. And so basically the way it works is that there's 2 gates that close with 1 actuator, and then we have purge, vent, and drain ports in between the 2 gates in different locations all the way around the pipe that you can remove the material and ensure that 0 leakage down the pipe. Another feature that we've introduced to this is the positive lockout tagout pin. And the way that works is that the lockout pin threads into the top structure, and there's a tapered edge on it that pushes on the top of the closed gates and ensures positive lockout. And so these are great, certainly in mining applications where you want to make sure or be 100% certain that there is 0 leakage beyond the gates. The next one that you see is our M81. This again is the same design style, however, it's meant for lower pressures. So this one's designed to MSS SP 81. It's more of a fit for purpose valve. However, it still has a lot of our severe service features to it, which is full round port, 0 leakage, shearing capability, full face flange is just meant for some of the lower pressures. So the one that you see at the top, that one, as we talked about earlier, all the way up to 1500 and even looking at 2500 pressure classes, because of our sealing technology, we can achieve those where other knife gate valves cannot. The next one is a low profile. Really, this is just our standard valve with a special engineered top structure for tight space constraints. So it really kind of highlights our ability to do engineered solutions based on your application in mining or any other industry as well. The transmitter isolation valve is really a unique valve that's designed to be bolted to the side of a tank so that the transmitting instrument can be removed, calibrated, or serviced without needing to drain the tank. So this is definitely a good valve that utilizes our technology for that. The next one is a paste backfill valve. So this one, again, is a unique design valve. We talked a little bit about paste backfill. It's a growing area in the mining segment. And this permits a reduced amount of material flow through and basically slows the velocity and the amount of paste filling a pipeline until it is completely full. And so what this does is reduces the potential catastrophic impact from paste descending vertically and reaching elbows and valves and other things and instruments in a pipeline. We offer control valves. And so typically people think of other types of valves for control. However, we're able to control the flow of valves by introducing reduced ports, perforated plates, V notches, and in controlling the actuation by throttling. So consider us for controlling applications as well. The next one is a rounded square that's used in a lot of different applications. A lot of people call them junk track valves, trash extractors, scavenger valves. And basically we took an old type of application that traditionally used, conventional knife gate valves and made it more of a guided shear gate, used our technology for high density cleaners and cyclones, or really anything, using pneumatic conveying processes. The through gate, again, we talked a little bit about that. You saw that in the history. And so we took our technology again and added it to a traditional through gate design and made it zero leakage. So using our sealing design to make something that's been around for a long time, zero leakage. These are traditionally used in blast furnaces or static column applications. So I would say we only recommend this type of a valve in 2% of applications because our guided shear gate is newer technology that eliminates the need for this style of valve. However, static columns where the media needs to be moved to the side and then put back is a good application for this type of valve.
Okay.
Trent, just real quick, there's a couple questions coming in on valve sizes. Can you touch on the larger sizes you're able to create? And also, are there diameter limitations by pressure class?
There certainly are diameter limitations by pressure class. It really depends upon the application specific. So in the lower pressure classes, as Dave mentioned earlier, we produce valves up to 48 inch. We're seeing more and more large bore valves. And so we often do, really, we consider anything, 30 inch and above large bore for us. And we do that on a regular basis. We do those in class 300 as well. When you get to class 600, 900, 1500 or above, there certainly are bore limitations for that just because of making sure that the gate can hold up to those pressure classes.
But I think too, Trent, I think we had an application at 60 inch that you guys felt that you would take a look at. So there's yeah, I think suffice it to say, bring us the large bore applications. We'll look at it and determine yes or no, and we'll tell you up front whether or not it could be done.
Yeah, I guess that's fair to say, Dave. We certainly can tackle larger bores. It's a matter of production, right?
Right. Yeah.
Get it done because it creates new manufacturing challenges for us, and there's always a way to get it done.
Sure.
So as you said, bring us the request, and we'll certainly take a look at it.
There was also, you mentioned the double block and bleed. There was a question around the drain connections, where they're located. I'll just take that. Essentially, on the clock face, 3 o'clock, 6 o'clock, and 9 o'clock are the standard port configurations. But those can be, I believe those could be moved around to suit the application.
They can. In standard, it comes with 3 of those locations, as you mentioned, but we've had some customers want to eliminate 1 or eliminate 2 for whatever reason. So we are an engineered product, and we do special requests like that if it makes sense for the application.
Okay.
And if I can just add, we didn't say how small we go. Surprisingly, we supply right down to 1 inch, and we have a number of valves, both in single block and double block, sold in Australia to one of the biggest miners in the world in 1 inch. See, quite a few. So normally the standard, the SP 135 standard is from 2 inch through 36 inch, but we can go above and below that.
Okay, just realize we're a bit tight on time here, guys. So we're just gonna, sorry. My first moderating in a while. I didn't do a very good job.
All right, well, we'll just zoom through this real quick. Obviously, you can see the design that, some of the things that we focus on is problems, right? There's a lot of problems with traditional knife gate valves. And so we've come up with solutions. One of the main points is that we have a full round bore. A lot of other knife gates have flats on the side that have a narrow gate. And so we increase the width of our gate to make full bore. And this eliminates turbulence, which results in erosion. So smoother down the pipe. Leakage to atmosphere is a big thing for us. And so we have transverse seals. So you can see there, Dave's pointing at them with the lighter gray strips are scrapers. So to the question before about scaling, these scrape off the scale on the gate and protect the seal to make sure that there's no leakage to atmosphere. True isolation during cycling. So we have elastomer seals on there, so you can see the dimple holes that are machined into our split body design, and these retain the seal in place mechanically so that there's no stretching, tearing, or deforming by the stroking cycle. Pipe stress is a big deal, especially when you get to larger bore. And so we've added a lot of body bolts to keep the body halves together and protect the primary and secondary seal, so that even when there is pipe stress, which obviously we want to avoid that as much as possible, we understand it does exist. So we've designed our valve to hold up to an acceptable amount of pipe stress. We could probably get into a whole side tangent on what that is, but we can talk about that at another time. And then the top structure of our valve is designed to hold a lot of different actuators. And we often see customers buy a valve, maybe with a manual actuator, and then they realize they don't want to use that actuator after it's been installed. The unique thing about our valve is that you can swap out actuators while the valve is installed under pressure, open or close. And our top works are designed to handle any different type of actuator: pneumatic, hydraulic, electric, hand wheels, gearboxes, and all those can be swapped out after the fact. And our design allows that. So something to be noted. Wear rings. We talked a lot about erosion and abrasion, and wear rings are an option that we put in. These are a cast ring that are indexable and removable. They prolong the life of the native valve body and is something that can be replaceable and changed out during routine maintenance cycles.
There was a question, Trent, in the chat about the wear rings. So they see them on the front, and sometimes we also put them on the back. What's done in between, and how do we deal with the rest of the valve body, and how do we protect the elastomers in those applications?
So the elastomers are retained mechanically by a machined groove. They're set out of the way of the flow path, however, minimally, so that there's not a big gap or a groove for media to build up. We also offer chrome carbide weld overlays on the rest of the body. The next slide shows that, where we don't have a wear ring. So you can see chrome carbide weld on there. It's machined up to the C area. We could do a wear ring on the face with this, both upstream and downstream, as Dave said. And then we also do tungsten carbide overlay, and we'll do that on the rings themselves too. So we'll do chrome carbide or tungsten carbide on indexable and replaceable rings.
The other thing too, I would add, is that you have a variety of elastomers, and they all have very varying degrees of mechanical resilience, if you will. And we've run into this for years in oil sands applications, specifications where customer has a service for a water line, but they mandate from a spec point of view that it has to be suitable for -50. Well, those two don't go together. So our argument has always been, we can design it for both, but it has to be one or the other if you really want it to last. The material that will work at -50 is not as strong as other materials that we have. But if it's in a service that's not going to see those temperatures, can we not make a determination that the process is more important than the specification? There has to be a way to write a spec to address those kinds of things. And we work, we quite often work in the engineering space with our clients on developing specifications that make sense for their business, which is really important. All right. I just want to touch briefly on this. CGIS has been at this for a long time. We are 43 years in business. I think Ross, or somebody you hired back then, had the foresight to start tracking the valves when we started selling them. So we have all of the application data on every knife gate valve that we have sold. So when you call and say, hey, I'd like to understand where you've sold valves in backfill or in uranium leaching or coal slurry or whatever, HPAL or feed, we have application listing that is very impressive, and I'm sure sought after by most of our competitors. So we have this information. It's obviously not for publishing, but we do use it, and this is where we get a lot of our information. We know what's successful and what is not. I think this slide was really just intended to talk about some of the key applications. Ross, you're going to touch on these case studies, so.
Yeah, touching is going to be right, because I think we are running out of time. So
Yep.
We've done a lot of work with some major mining companies over the years that most of the things that we do, they like. So they keep bringing us in to see what else can we do. And this picture on the right is double block and bleed valves for sulfuric acid. No, it's no solids. It's just straight sulfuric acid at various concentrations. So our alloys are different alloys that resist the different concentration and temperature of sulfuric acid. But what the company wanted was a valve that they could trust for their worker safety. So that's the one on the right, but the one on the left, I think, is even more impressive. When we got to this plant, it's a very unusual mine, copper, gold, and uranium. I don't know how in the world this could be a mixture, but it is. And it means that their tailings are radioactive slightly. Well, if you're a radioactive tailings, that means you have a responsibility that may go well into the future for you to make sure that that radioactivity doesn't get outside of your containment. The valves they put into their 16-inch class 300 pipe system when we first got there were a push-through knife gate valve. All the pictures you've seen of valve failure, I want to be very clear, we don't think any of them are bad valves. We think they're the wrong valves for the application. And in this case, what was happening, the number of cycles of the valves in the tailings disposal system were cycling enough that the sleeves that they were having, because they were a push-through knife gate, were failing within 2 to 3 months on average for years. So every valve had to be re-sleeved. And now you got these 15 kilos of rubber that's radioactive. What do you do with it? We came in and said, well, we don't think that life cycle is very good. We're going to give you a valve that we think will last years instead of months. And they bought it and they put it in. And if we fail, which we hadn't for 2 years after they looked at it, if we fail, then our volume of seal that's damaged is going to be 1/100th of what the sleeves were. So it was a way of fixing a big problem. We became very, very well liked because of that. And what it's done today is given us, I think, one of the most unusual orders in history for a supplier. We were allowed to design the valves for their massive project in Canada in a potash mine. So we got 100% ability to design and then we got the valves. So it helps, I think, by being embedded, by getting into your customer as a partner, not as a vendor. And that's one of the secrets I think we've learned. We want to be tighter. We want to take more responsibility. If we fail, okay, we'll own it, but we try not to fail, obviously, and have a great deal of success. This is the second case study where we challenged history. You know, history gives us a perspective. Oftentimes, if you do what you did yesterday, you're not going to go wrong, but are you going to go right? And this is a case where we looked at a filter press. This is the biggest filter press in the world, mezzo dewatering press, that used a technology, the push-through knife gate valve, that again, on average, caused them to replace the sleeves every several months. They were cycling from between 70 and 90 times a day, which is way beyond the ability of a push-through knife gate valve to handle. It was never designed by Clarkson in the beginning to have many cycles, to have very much pressure. It was a 10 bar or 150 PSI valve, low cycle, neutral pH valve. It's being pushed way beyond its design. We put in our valve, and again, it lasted 2 years before it had any issues, and all that meant was you had to tighten the packing. Much, much better OPEX. And I think we don't have time to go through this, but we can share this with anybody who wants to look at it, because the case study was written by the owner. He came and said, I can't believe that this is so much of an improvement. So we'll just keep going.
Hey, Ross, just to chime in, people are able to drop off if they need to go to other places. We will be sending out a recording. So I think maybe go through it. If those are interested, you can keep going.
Okay, well, I think if we go back to what this application is, it's a filter press. And so the valve is going to cycle a number of times. And this is the number of cycles that is the handicap. This is the part we have to really know. Again, very carefully, I want everybody to understand, I think the Clarkson KGD is a very good valve. I think the Clarkson KGA is a very good valve. But when Clarkson invented them, he had in his mind what they should be used for. And unfortunately, where I see the issues, like that one that was free discharging, that acidic mixture from the fourth floor of the building in the Caribbean, that's free discharging. The valve was fully open. It wasn't closed. It was fully open. It didn't discharge. It was allowing that process to come out a sleeve that didn't join with the other sleeve. So there was a gap in its system. So we have a different design. Trent has put his valve to be extremely high cycle. Again, that's a word that's subjective. What does it mean? Well, it means in the case of a push through versus a guided shear gate, if we just do generics, the guided shear gate has a capability of being at least 10 and often 50 times higher cycle life. So even if the valve was 2 or 3 times the cost to buy, it'd still be cheaper. So this is a part that we really want to understand and to offer. We have to be careful of CapEx, obviously, but OpEx, what it costs you to operate, not only just to replace the valve, but what process production do you lose? Every time you have to change a valve, you have to stop the process. But we are very careful about that. We want to focus on where we're best, and a filter press is one of those really great applications.
Okay. There's just more pictures of that. There was a question, can we get the filter press case study? Yeah, the answer is yes.
Yes.
Sam's going to send that out.
Yes, and it's been, unfortunately, it's been cleansed of the owner by the owner's wish. He didn't want to be known as somebody who had this problem for 5 years before we came to it. So we have to accept it. I think if you look at the case that was written by himself, you might be able to get some clues.
Okay.
I have just a question here. Again, no bad valve, but the whole world right now has got ESG on its mind, and every mining company that I see in the website, one of the first things on their pages, we are ESG sensitive. Okay, then please explain to me how you can use a valve that discharges on every stroke. I just want to know that question, because I don't think it's possible. And we've internally done a study with an outside source that's can you back that statement up? Can you say that's true? And we can provide a document that's from a third party that says this is true. We're side by side comparison. Which one's better? The guided shear gate doesn't discharge. And if it's packed properly, which we normally do, and we can teach you how to repack it in service, it doesn't have emissions. So it's tight. Everything's inside the pipe. Ross,
there's a couple questions that are still outstanding. And guys in your chat group, I don't know if you can see, but VG's asked a couple questions about oil sands applications. And so they had issues with metal seated valves, of course, they wouldn't shut off. And so they've gone to a dual resilient and metal seat, but they're having some issues in the resilient seats in some tailing services. Understand the way the valve is built, and Trent alluded to this earlier, the two body halves come together and they wrap around that seal. They expose a small area, about 20 to 25% of the surface area, the seal. We use the wear rings to deflect the process away from that seat. But I will say this has been a challenge in oil sands for a number of years. And this is where the opportunity exists to really look at different seal materials that are capable fully of living through -40, -50, and being able to operate. They're not going to seal as well at that stage. It's not a catastrophic failure, but I think this is a specification question that's been challenging for the oil sands for a number of years. They're allowing the -50 spec to preempt the need for the seal to last as long as they might want. And so it's been two sides of the scale for sure. But we've had great success. We've, as I mentioned, Trent's got about 5 or 6 different materials today. And I know I was speaking to their head of engineering last week, and they are looking at some alternate seal materials today. And I will say the seal and elastomer space is like any space. And in the last few years has gone through tremendous growth, and new materials continue to come to market every day. So we'll continue to explore those. But give us a call. We've sold literally thousands of valves, more than 10,000 in oil sands specifically. So, and I spent 25 years selling in that market space, so we understand that space quite well. And then Lennon has posed a question around the Volcan Peru filter press application.
Yes.
He found Rocca incrustations in and around the primary seat. So how could it be avoided, or what materials could be used? Will this cause the valve to cavitate and erode it?
Okay, if this is Volcan Chungar, it's a very good case study, one of which we supplied originally for a filter press from Mexico, but an American company called Micronics, I believe. And this was sold through a local Peruvian distributor who wasn't able to provide all the information that we would have liked normally, but it was good enough. And so we supplied them some valves. They were installed, and then fairly shortly thereafter, we started to get complaints. And our Latin American sales manager, Tony Zapata, flew down to say what was happening. And what we learned was that we weren't responsible for the air delivery system. These were pneumatically operated valves. We were not responsible for hooking them into their air system. And when we were showing the pictures, and then Tony was there, what we found was that the air tubing was what I call spaghetti tubing. It was really undersized. It was a tiny amount of ID to deliver the air to these actuators, and the CV of the pilot solenoid was tiny. So what did it do? Instead of giving enough air to push the piston in the actuator so that the valve would cycle, in an 8-inch valve, we'd like to see no more than a second an inch at the worst, but half a second would be better. So 4 seconds to cycle. Well, they were taking 45 seconds to a minute to cycle. And what that turned the valve into was from an isolation valve to a slurry control valve, which wasn't what we sold it for. So we said, okay, we understand what you got here, but can you make these changes? Can you give us bigger air tubing, and can you give us a higher CV solenoid? And that's being done. And as I understand from Tony, who's just on his way back from Madagascar today, they're all happy again because the valves are doing what we said they were doing. So this is a great maybe story about we don't give up. We're not perfect, but in this case, we were blamed, and we accepted that you could blame us until we could prove ourselves innocent, and we have. So, but I haven't followed up with the incrustation.
I just want to add to that because the question was around as well, the presence of solids. So I could tell you some of the simple changes we've made over the years is, can the valve be relocated? In some cases, the valves are in this orientation, and so gravity is going to make for material to settle in the bottom of the valve. Now, as Trent demonstrated, and we have literally tens of thousands of installs to prove it, the valve will displace that material as it strokes. And the very small particulate that is there may get trapped under the flat tip on the bottom of the gate. That will happen from time to time, but that's fine. It is squeezed down onto the metal-to-metal surface, and the valve will still close and will still seal reliably and repeatably. But in some cases, we've said to the customer, can you move the valve to a place where the valve is in a vertical position so you get rid of the solids just by gravity? There's simple things that could be done like that.
Or turn it upside down like we did in the oil sands many years ago. And now the rock that's on the bottom of the pipe is pushed off as the gate goes up.
Right. So there's always ways to deal with things like that.
Yeah.
One other quick kind of question: how do you prevent compacting of debris at the bottom of the gate? Is there a flushing option? That was just another question that was hiding.
Yes, there are flushing options. And that's a very good point. And there are some applications we've struggled with as we didn't understand how products amalgamated as they were compressed. One I'm thinking of right now in Trail, British Columbia, was on zinc powder, and the zinc it was a powder, amorphous, and then as we closed it, we turned it into a solid piece of metal, and eventually we couldn't close it. Didn't have enough horsepower. But as Dave said, and Trent has designed, we can put this valve in any direction on a horizontal pipeline, 360 degrees around that pipe. We would prefer not to put it in sideways on a horizontal pipe. That's the least preferred, but acceptable. But that's the least preferred because now we got gravity operating differentially on the bottom of the seal instead of the top of the seal. But vertical up, vertical down, beautiful. Obviously on a vertical pipeline, we don't care any direction, but it's a point we should have more conversation, and maybe we can solve this prior to you putting it in by learning some more things. I was on a call this yesterday in Brazil where they've got a requirement for a high pressure, large 18-inch class 600s, but they must be manually operated. Well, a gear operator to manually operate that valve at 18-inch 600, which is above my height, is not going to be simple unless we put a big gear reduction in there, which means there's going to be a lot of rotations on a hand wheel. How friendly do we want to be to that poor operator who's going to go out into the Brazilian jungle and be there for an hour and a half? We have to think of all those things. But when I learned from the guy yesterday that, oh, well, this is only going to be maximum one time a month and only for 3 years. Okay, that's doable. Now we can design specifically for that. We have another technology. We have a gun, an electric gun, or sorry, battery operated gun that will do all that heavy work for him. So ask questions, learn, and we go.
Good. Okay, we're going to just wrap up on the last slides here. Ross, you mentioned about this you got into the ESG discussion. So this is becoming more of a challenge. And we do expect that we're going to be able to, in the not too distant future, we're really going to drive the industry with an ESG statement that is unique and will be a first of its kind in the industry. So we're excited about that coming down the pipe here shortly. Yeah. Again, here's some oil sands valves that so we these challenges continue to go on. -50 is always the problem that we're looking at. So we want to continue to talk about these applications, but as I mentioned, we've got in excess of 10,000 valves in oil sands. So we know this business very well. Cost of ownership, Trent, some of your guys at the shop, got various sizes, particle sizes, some of the things that we handle. So we don't really care what the rock looks like, how big it is, how many there are. We can handle all those different applications. At the end of the day, and Ross mentioned this earlier, the challenge is always the CapEx discussion. Do you want to spend a little bit more and get an upgraded valve, or do you want to make some future changes that could make the valve better and better over time? This is a very common practice. We'll see an application where the valve lasts, a competitor's valve might last 3 to 6 months. We'll put a valve in, it'll last 2 to 3 years. And then the next question is, okay, how do we go longer? And so there's always options to add. So thank you for listening. There's our emails on the bottom. Again, my name is Dave Friesen. I'm the president of CGIS and past sales guy, and always a sales guy at heart. Ross Waters, the director of CGIS of 50 years selling valves or more, and Trent Runyon, the president of DSS Valves. So thank you, Trent, for your time, and Ross, appreciate it. And for all the great questions.
Yep. Thanks, guys.
Thank you.